So, dear colleagues from all over the world, it is a pleasure to welcome you to the 17th conference of the TAUP series. My name is Mariam Tortola, and I am the co-chair of the local organizing committee of the conference, together with my colleague Sergio Pastor. This conference was supposed to be held in person in Valencia, Spain, and I'm sure most of us would have preferred it to the online version. However, the COVID pandemic has made the in-person event impossible. And here we are, attending the first fully virtual TAUP conference. Hopefully, it will also be the last one as well, although we all know that hybrid events will become very frequent, at least in the near future. Other members of the local organizing committee would like to give you their welcome message as well. They will do it in this video.
TAUP is back to Spain again, so bienvenidos, welcome, bienvenidos, greetings from Zaragoza.
Welcome to TAUP 2021 from this beautiful town, Santiago de Compostela.
Welcome to TAUP.
Benvenuti a TAUP 2021.
Welcome to TAUP 2021.
Καλώς ήρθατε στο TAUP 2021.
Bienvenidos al TAUP 2021.
Willkommen zu TAUP.
Benvinguts a TAUP.
Welcome to TAUP 2021, the hottest conference in the coolest possible place. Hope you enjoy it.
Welcome to TAUP 2021.
So we are sorry that you will not be able to enjoy Valencia this time, but we are sure that you will have other opportunities to visit our wonderful city in the future. For those of you who don't know Valencia yet, the following video shows some of the essential places the visitor cannot miss. Okay, so let me introduce now Professor Núria Rius, Director of our Research Institute, IFIC. So please, Núria.
Thanks, Marianne. Good evening, Asia and Australia. Good afternoon, Europe and Africa, is somebody there. And good morning, America. On behalf of the IFIC Institute, I want to welcome you to this 70th edition of the TAUP conference, which, as Marianne said, it was meant to be held in Valencia this year, but due to the COVID pandemic, has been kept online. IFIC is a joint institute of the University of Valencia and the Spanish Research Council, which has its origins in 1950, so we are quite old. It is devoted to the research in nuclear particle and astroparticle physics, both in experimental and theoretical aspects, and also technological applications. The field researchers has been involved in this conference since the very beginning, back in 1989. In the first years, as you know, this conference was mainly alternating between Italy and Spain, and later on it was extended the venue to many other countries in Europe, Asia, and America. So we were really looking forward to the possibility of having TAUP in Valencia this year, and it has been a pity that it's not possible. I want to thank the organizers for making this online conference happen, and for trying to have a conference as lively as possible, given the circumstances. They were keeping open the possibility of having a face-to-face conference till the last minute, but finally it was clear that it was not possible, and I think this has been the right and safer option. I hope that it will be possible to have another edition in person in Valencia in the near future, so you will enjoy all the social aspects that you just have so and are missing. I also want to thank all the speakers for the effort. I know it's not the same to have a conference that to do this from home at different times, not very convenient sometimes. And also all the participants. I'm sure it's going to be a great success, thanks to all of you. And without more delay, let's start with the interesting physics of this meeting. Welcome.
Thank you very much, Nuria, for your words. So now Professor Juan Fuster, so he is a researcher at IFIC, and he is also the current regional delegate of the Spanish Research Council, CSIC, in Valencia. He will also welcome you to the conference on behalf of the CSIC president. So please, Juan.
Well, good morning, as Nuria said. Hello, Nuria. Good morning, good afternoon, or good evening, wherever you are. It is my pleasure to welcome all of you, all the participants to the conference on behalf of the Spanish Research Council, as the conference on topics on astroparticle and underground physics TAUP, a reference conference in the field, which is under the auspices of UPAP, the International Union of Pure and Applied Physics. This time I have seen, in fact, that your scientific program is intense, broad scope, and very exciting, covering cosmology and particle physics, dark matter and its detection, neutrino physics and astrophysics, gravitational waves, high energy astrophysics, and cosmic rays, so almost everything. So CSIC, as explained by Nuria, concerning CSIC, yes, IFIC is a joint institute belonging to the University of Valencia and the Spanish Research Council, the institution I am representing. So CSIC is the largest scientific institution in Spain, and one of the few belonging to the central administration, which is present in all community regions in Spain. And it's not the police, and it's not the army, and so it's for science. In the community of Valencia, CSIC counts with 11 institutes, which cover biology, applied biochemistry, physics, neuroscience, food technology, climate and desertification, marine science, biomedicine, and so on. So 8 of these institutes are joint projects with the universities, as it is IFIC, and 3 of them belong to CSIC entirely. Can you see me? Yeah, okay. So IFIC, as Nuria, I am a member of IFIC, so I also have to defend, to have the flag of IFIC. So yes, IFIC is of the largest and most recognized institutes, not only in Valencia, but also in the Spanish landscape. And here in Valencia community is the oldest institute of CSIC, as it goes on the early 50s, as Nuria also mentioned. It's well balanced, having around 50% from the 2 institutions each, so CSIC and university, and also has an extraordinary good equilibrium between experimentalists and theorists, which I think is one of the most recognized strengths of the institute. Members of IFIC, like Professor Bernabeu, were at the origin of this conference, at the TAUP conference as one of the organizers already in 1989 in its first edition. Here I would also like to mention a few words to remember Julio and Angel Morales from the University of Zaragoza, who were at the core of this conference from the very beginning, and the promoters of the underground laboratory of Confra. So this states, I think, the strong commitment and close relation of the Spanish community to this conference. On the organization, well, you both mentioned already the present COVID-19 situation we are living is very peculiar and gives us very difficult times, no? Especially to organize this type of events, which essentially make very difficult to travel among the different countries. For these reasons, I would like to thank the organizers of the conference for keeping it and maintaining the program, even if it is in a virtual format. I believe this is important for all, but especially for the youngest generations, allowing them to show up their results. Special acknowledgements to Sergio Pastor and Mariam Tortola, of course, the chairs of the conference, but also to all the other members of the organizing committee and the rest of the Spanish group supporting the conference. I believe all of us recognize the generosity and the effort demanded to organize such a conference with more than 600 participants in the present situation, where most of the hard job remains the same as for a normal conference, but without the reward of the in-person attendance, no, of the participants and all the human and scientific contact and benefit which comes attached. So on the scientific program, as I said, it is very complete, and I see many familiar names in there, which it would have been very nice to meet them. But in any case, I am completely convinced that the conference will be a success and plenty of interesting discussions under the virtual conditions. I say also that we will have a public talk that will be in person, which will be presented by David Garcia Cerdeño, who is an expert hunter of that matter. So I'm completely sure you will enjoy this talk. And yes, just to finish, as Nuria said, what can I say? I really wish that you have a very successful conference and hope that we can see many of you in Valencia whenever possible, sometime in the future. Thank you.
Okay, Juan, thank you very much for your welcome message and for your nice words. So finally, Professor Maria Vicenta Mestre, Rector of the Valencia University, who unfortunately was unable to be with us live today, will participate in this welcome session with a video.
President of the Spanish National Research Council, Professor Rosa Menéndez, Director of the Institute of Corpuscular Physics, Professor Nuria, co-directors of the local organizing committee, Professor Mariam Tortola and Professor Sergio Pastor, dear members of the local organizing committee, dear friends. Good afternoon to you all. 2 years after the conference in Japan, the meeting will be in Valencia, organized by our Institute of Corpuscular Physics. I am very pleased to participate in the opening of the 17th conference. It is an opportunity to recognize your scientific work, courage, and determination. Our Turia city will have been an excellent place to hold this event. In our conference center, as was planned, and with ceremonies in historic buildings of our university, which was founded more than 520 years ago. With other more modern buildings, such as our Science Park, a regional, national, and international hub for attracting potential scientific and business talent. I sincerely hope that you bring about scientific advances in the great challenges of astroparticle physics in the present, but also in the future of world science. In the knowledge of neutrinos, a particle that poses numerous scientific, theoretical, and experimental challenges. In the important work of discovering the nature of dark matter, key to understanding the evolution of the universe. In the observation of the universe thanks to thriving multi-messenger astronomy. In the study of black holes, essential for advancing our understanding of gravity in the most extreme situations. I would like to recognize the great advances of which you are knowledgeable and in which you have even participated. Small steps, such as when the collision of a neutron star and a black hole was caught for the first time a few weeks ago. Challenges that you understand and for which you are largely responsible. Astroparticle physics has great challenges to overcome. Bringing this conference to Valencia is a great reward for the effort made over more than 2 years. Congratulations and thank you. Professor Pastor, Professor Tortola, colleagues, congratulations. I would like to express our desire to be able to hold this meeting in person as soon as possible, to get back our contact, face-to-face meetings, coffees, the most emotional part of science, but I also want to recognize that the virtual setting of the tables, presentation and papers is the result of the effort made by many people and of the ability of the local organizing committee and all of you involved in the advancement of knowledge. Therefore, I would like to thank once again the Institute of Corpuscular Physics and all of you who are responsible for its success. The greatest advances such as health, energy, sustainability, and new technologies will come about thanks to your work, your effort, and your ability to see what others can hardly imagine. For this, I would like to share with you my admiration, my congratulations on your success, and my encouragement for you to continue to lead scientific and human progress. Congratulations and thank you.
Okay, so now the other TAUP 2021 co-chair, Sergio Pastor, will present a brief introduction to the conference. Please, Sergio.
You are muted, Sergio.
Okay, now you can hear me? Okay, sorry. That was just, everything was too perfect. So thank you, Nuria. Thank you, Juan. Thank you, all of you. And as co-chair of the TAUP 2021 conference, I would like to welcome all of you to our meeting. Unfortunately, not here in Valencia, but an online conference doesn't mean that should be a world conference. So this is why, and hosted by the Institute of Corpuscular Physics, that, as was said, is a joint institute of the University of Valencia and CSIC, and with the help of the local organizing committee, which is composed, as you can see here, but many people from IFIC, but also from other people from other groups in Spain, including the University of Valencia, CIEMAT, IFT Madrid, the University of the Balearic Islands, Alcalá, Zaragoza, Granada, and Santiago de Compostela. Some of them, you already saw them in the video, yes, welcoming you. 2 years ago, so we were granted the organization of this conference, so we started to prepare with the LOC, the conference, and unfortunately, we couldn't have the in-person meeting as planned, and as was said already, We tried even with a hybrid event until the end, but it was not possible. So with the support of our institute, University, CSIC, and Tiamat, and with the kind of sponsorship of UPAP, we will have a TAUP online. Now, with the sponsorship of UPAP, let me remind you that any participation must follow the conference policies of UPAP, including the code of conduct. So no discrimination, harassment will be allowed. This was what we planned to, a standard TAUP conference format with invited plenary talk, parallel sessions, including the talks selected by the conveners, and poster session. And as you can see here, this is what was done in Toyama a couple of years ago. Now, we cannot have this, and with the help of the TAUP 2021 International Advisory Committee and the TAUP Series Steering Committee, we have organized an online conference which, taking into account that this is a truly international community, we should fix the times of the parallel session, the times for the other contributions. So what finally we arrive is, let's say, copying what other conference did and trying to organize in the best possible way. We will have a plenary program consisting of inviting plenary talks in the morning, afternoon, evening, and American, European, Asian time. This will be a live program starting just now in 10 minutes. We will start usually at around 2 p.m. or 1:30 in Central European summertime. Then the problem was with the parallel sessions. And as you could see in Toyama a couple of years ago, we are talking about several hundred talks. This year, we also have several hundred talks, actually 300 talks, which means that we couldn't have all of them live. It will be too difficult to adjust the time. So what we did is to organize this as all parallel session talks will be pre-recorded, and we have seen that almost every author of a talk has submitted the corresponding video to YouTube, and we have linked all these videos through our Aula Virtual, this virtual venue webpage, and also our Indico. So I would like to encourage all of you to see these talks. Just select the section you want to see, select the authors, and then you will be able to ask questions or comment with the authors in live discussion panels, which will happen from next week. A few of these parallel session talks will be held live in the so-called hot topic sessions. We'll have a few of them just before the plenary sessions tomorrow and also next week. And finally, we will have poster sessions that will be held in a virtual on interactive platform. So, as usual in a TAUP conference, we have people that serve as conveners of the parallel sessions. And this year, we will especially like to thank all of them because they have worked much harder than in a standard TAUP conference. First of all, because of the deadlines. Since we only decided that the conference was held online at the end of May, it means that all times were shorter than usual. So they have to decide on a very reduced time. They have also organized all the sessions. They have organized the discussion panel. So thank you very much to all the conveners. You have 1 page or 2 guaranteed for the future. So this is the main program scheme of TAUP that you probably already see. So we have converted a Monday to Friday conference into a 7-day conference, avoiding the weekend. You can see here. Now in green, you can see the plenary talks. In yellow, the parallel hot topic sessions. We will have 3 or 4 every day. And finally, from Monday until Thursday the next week, we will have the discussion panels, which also will run parallel. And the 2 poster sessions on Monday and Wednesday. Now, for each of these sessions, we will use a different platforms. So Zoom for plenary, Blackboard Collaborate for hot topics, and discussion panels, and GatherTown for the poster session. So this is probably a bit of a mess. And we also apologize to all the participants because sometimes our instructions were not completely clear, and also about the deadlines and everything. But the best thing is that you simply connect, as you did now, with the virtual venue, so you should have received your access credential. Go to the 17th International Conference on Topics in Astroparticles and Underground Physics, and from there you can access to any of the talks, any of the sessions, and the corresponding platform will open automatically. Now, concerning the plenary sessions, and after each of the talks, we would like to have your questions, so please include them in the chat, and the corresponding chairperson will select them. Of course, there will not be time for all of them, so for each year, you could see that you will have a forum that you can use for further questions and comments. The poster sessions on Monday and Wednesday will be in GatherTown. I'm sure that many of you have already used this. So thanks to our student Paulo Martinez Miravé, he has created this world in GatherTown that we would like you to enter, explore. You will see the posters there, and especially on Monday and Wednesday. And it's also full of surprises. So please use it even if it is after or before the poster sessions. We also have the Twitter account. So thanks to Avelino Vicente. So we'll post many of the updates there. And finally, also a poster preview webpage that you can see here, where you can have a preview of all the posters, and you can also check that where the corresponding room for the poster session will be. So that's all. And as was already said, let me emphasize again, this is not the TAUP that we wanted to organize, but we really hope that will be one of the best TAUPs ever. So to all registered participants, over 1,000 at the moment, enjoy TAUP 2021, and we hope to meet you soon in Valencia. And with this, I close the welcoming session, and I'll give the session to the first chairperson, Sandhya.
Hi, Sandhya, I don't know, I think you are connected as a participant. So I just send you in the chat the link to connect as a chairperson. So if you hear me, perhaps you can do it, or maybe the host here in the Zoom session can change your status.
Hello, Mariam, are you talking to me?
Yeah, perfect, great.
Because I actually left that room and then I used the other link to.
Oh, great, perfect, thank you. So your turn is.
So nice to see you. It was a very nice starting session.
Very good. So please, you can start already the first plenary session. Thanks, Sandhya.
Thank you, Mariam. Thank you, Sergio. So hello and welcome to everyone who has joined us for this first session of hopefully the only online TAUP conference that we will have. We will be listening to, of course, like Sergio showed us, to a very large number of very exciting talks spanning a very wide range of topics in particle, astroparticle, and cosmology. So it's a pleasure to kickstart this conference with this first session, which is on neutrino physics. And we'll have two talks in this session. And I invite Raymond Volkas to tell us about neutrino theory and start this conference. Raymond, will you share your screen now?
Yeah, thank you. And I hope this works the first time. Let's see how we go. Okay, hopefully
we can see it.
Okay, so honestly, thank you very much for the invitation to give this talk. I really, would have hoped to be having a nice crisp El Barino in Valencia, but it's not possible, so never mind. So what I want to talk to you about today is the fact that there are literally thousands of neutrino mass models that are worth considering. So let me get on with it. Okay, so after an introduction, I'll then move on to the longest part of my talk, which will be to talk about a catalog of Majorana neutrino mass models. And in this talk, I will specialize to the Majorana case. If Dirac neutrinos were added in, the number of models would be even greater. After discussing that catalog, I'll then talk about an interesting connection that exists between a lot of the models in the catalog, not all of them, but a lot of them, with other anomalies that have gained a lot of notoriety in recent months and years, namely the G-2 anomaly of the muon, and also B Meson decay anomalies, and then there will be closing remarks. All right, so we all know that the discovery of non-zero neutrino masses through the heroic experimental efforts that discovered neutrino flavor oscillations proves that the standard model is incomplete. We need some mechanism by which the neutrino masses and mixings are generated. And what I would really like to know as a theorist is what that mechanism is. And we really, at this point, have no idea. And uncovering what this mechanism is probably a very long search unless we get very lucky. However, what I would like to, a theme of this talk will be that very important clues, even if not, complete evidence about what the mechanism is, at least very important clues can be obtained on a relatively short time scale. And I'm thinking of things that include results of neutrinoless double beta decay experiments. If double beta decay with zero neutrinos is ever observed, we'll know that delta L equals 2 processes happen, and that will be very important, whether or not that's directly correlated with neutrino masses or not. Charged lepton flavor violation, there's a lot of efforts happening there in mu to E conversion, mu to E gamma, mu to 3E. And you would expect, since neutrino flavor is not conserved, the charged lepton flavor would also not be conserved. And if that was observed, that would be important information also for neutrino mass models. A theme of this talk will be the flavor non-universality anomalies in RK star and RD star, and I'll come to that later. And there's also anomalous magnetic moments for the charged leptons, particularly the muon, and to some extent the electron. And so these involve new interactions for charged leptons, and those new interactions can also have implications for neutrinos. So one of the takeaway messages I want from the talk is that the neutrino mass problem is part of the general flavor problem of why we have 3 families and all the rest of it, and hierarchies of masses and mixing angles, or not hierarchies as the case may be. And I want to talk about the fact that the charged fermions can actually help us in the neutrino mass problem. Before I get to the catalog, I just want to set the stage a bit with other strong evidence or even incontrovertible evidence for the existence of new physics. And the first one is the existence of dark matter. And that will be a major theme of this TAUP meeting. So we can ask the question, are the neutrino mass and dark matter problems connected? And the answer is they don't have to be, but quite possibly they could be. And a rather famous class of models are called Scotogenic models, where dark matter helps to generate neutrino mass at loop level, started by Ernest Marr quite some time ago. And there are, it's a really active area of investigation. So it could be those 2 pivotal problems that prove that we need new physics could be connected. And then there are what I call empirical near proofs from cosmological fine-tuning, the matter-antimatter asymmetry of the universe, and then the problems of hot Big Bang cosmology, homogeneity, isotropy, flatness. We can also ask, are one or both of these connected with neutrino mass? And again, the answer is possibly. They don't have to be, but they could be. And famously, there's the leptogenesis mechanism of Fukugita-Yanagida, and that's a way that neutrino mass generation is directly connected with the matter-antimatter asymmetry problem, and that's a very exciting potential connection. There's possibly some connection with inflation, although that's less clear. I would like to mention very briefly just one class of models where these are axion models solving the strong CP problem, where the Peccei-Quinn scale is identified with the type 1 seesaw scale, and this permits the problems of neutrino mass, dark matter through axion dark matter, leptogenesis, and even inflation to be interconnected while also solving the strong CP problem. So, it will be interesting, eventually for somebody to understand how many of these problems are completely independent or possibly related. Okay, so two big questions, not the only questions, but two big ones for neutrino mass modeling is, first of all, are neutrinos Dirac or Majorana? And then secondly, why are the neutrino masses so very small, less than about 0.1 eV, at least 6 or 7 orders of magnitude smaller than the mass of the lightest charged fermion, the electron, and even much less massive than the heavier charged fermions. As I've already mentioned, for this talk, I'm going to stick with Majorana neutrinos only. Dirac neutrinos are also interesting, but I can't talk about everything. And I've worked mainly on Majorana neutrinos myself. Given that assumption, I will then talk about the second issue of why neutrino masses are so small in detail. I want to apologize that I won't be able to cover the very large and interesting literature on flavor symmetries, except to note that later on, when we talk about the flavor anomalies, even though I won't be able to talk about this fully, flavor structures are important, and the ongoing exploration of flavor symmetries is very important and very relevant. Okay, so now let me move on to the main part of the talk, which is this catalog of Majorana neutrino mass models. So basically, we seek, can you see my cursor, Sandhya?
Yes, we can see your cursor. It's working well.
Great. So we have the standard model Lagrangian, minimal standard model Lagrangian, and we seek an extension to that, some other Lagrangian that we add to it, that contains the standard model fields, some new fields, some parameters, both mass parameters and dimensionless parameters, that might also be mass ratios, and where this Lagrangian for the Majorana mass application violates lepton number by 2 units. And basically, we want to know what this is. In order to, so now turning to the main problem, which is explaining the tiny neutrino mass, you can imagine 2 different contrasting limits whereby small neutrino masses are correlated with the properties of this additional Lagrangian. So in the first case, which is what constitutes seesaw model, we have a very high scale of new physics, capital M, much greater than the electroweak scale, that induces delta L equals 2 processes. And as we take that scale to infinity, the neutrino masses go to 0. So there's this seesaw relationship, and L conservation is restored as the new physics decouples in the UV, meaning the new physics becomes very heavy. And the smallness of neutrino masses is correlated with that near decoupling. Or you could have inverse seesaw models where instead a small dimensionless parameter, there's a small dimensionless parameter, and when that goes to 0, the lepton number violation by 2 units goes away, and neutrino masses also go to 0. And this is the general class of inverse seesaw models. For the purposes of this talk, having provided that sort of oversight, I'm actually going to focus on seesaw models and also radiative models, which are really hybrid models between seesaw and also, potentially having some small parameters. Okay, so if we want to do a survey of the general class of Majorana models, how are we going to do that? We need a systematic tool, and the systematic tool is effective field theory. So what we're interested in is effective operators, gauge invariant effective operators constructed from standard model fields that induce lepton number violation by 2 units. And these operators are going to be non-renormalizable operators, so they're going to have mass dimension greater than 4. And famously, the late Stephen Weinberg realized that at mass dimension 5, there's a unique class of such operators, which we now name after him, called the Weinberg operators. And these involve 2 lepton doublets and 2 Higgs doublets. This is the dimension 5 operator, so there's a 1 over m, where that's the scale of the new physics. And this violates lepton number by 2 units. And it is interesting that at mass dimension 5, the first non-renormalizable mass dimension, you immediately get an effective operator that impacts on leptons, and in particular on neutrino mass, because there's a Majorana neutrino mass term hidden in this effective operator, as I'm sure you all know. Then there are also generalized Weinberg operators where, in addition to the typical LLHH structure, you also add some power of H dagger H, where H is the Higgs doublet. And these are called generalized Weinberg operators, and they're also of interest, and this is what the Feynman graph looks like. And so what we're interested in is what is this new physics, this delta L equals 2 new physics that occurs at some at some mass scale m and is ultimately responsible for neutrino mass. And from the generalized Weinberg formula, this is the kind of expression you get for the neutrino mass. So it's suppressed by the small ratio of V, the electroweak scale, divided by big M. And depending on which Weinberg operator we're talking about, we may have powers of that. Also, we can have dimensionless coupling constants, products thereof, and they might all be, you know, smallish, 0.1, 0.01, something like that. And we have a product of them, and that can also help suppress neutrino mass. Okay, so these Weinberg operators, which violate delta L equals 2, directly produce neutrino masses. You just stick the VEVs into the Higgs doublets and you get neutrino masses right away. But they're not the only operators constructed out of standard model fields that are gauge invariant that violate lepton number by 2 units. And in this talk, I'm going to consider this general class of delta L equals 2 operators in their own right. Not just the Weinberg operators, but all delta L equals 2 operators. We're going to list them, we're going to classify them, and then we're going to connect them with neutrino mass afterwards. In other words, we're going to ask what is inside this blob that gives us this delta L equals 2 physics. So in terms of doing a systematic classification, you can either study the Weinberg operators directly, or you can study the more general operators first and then connect them with Weinberg operators afterwards. Both approaches have been pursued in the literature, and they're complementary approaches. The Weinberg operator classification scheme has actually been done by the group in Valencia. And I refer you to some of the papers down there. And this is a very deep and complete and interesting body of work. The other approach, which makes the connection with Weinberg operators as a second step, which is the one I'm going to talk about, was started by Babu and Leung about 20 years ago, followed up some years later by de Gouveia and Jenkins, and over the last decade, I think, mostly pursued by my group. And you see a bunch of former students, current students, former postdocs there in the group, and a bunch of our papers written over the last 10 years or so. And there's one in red because this is the one with my ex-student, John Gargalionis, that I'm really going to highlight. And I should mention that a year ago, he should have started as a postdoc at Valencia, but unfortunately, the pandemic has delayed things, but hopefully that will start soon. All right, so what do these operators look like? Well, there are a lot of operators, and they've been written down explicitly up to mass dimension 11. So here are some of them. You see all sorts of weird and wonderful operators there involving standard model fields and certain weak isospin contractions and so on. Color contractions are not shown explicitly. You see various columns that I will explain later on, models, filtered loops, lambda. Well, there are even more operators. I've omitted 4 pages of them, but anyway, if you look at this paper, you will, and some of the earlier ones, you will get the full list. This includes operators also with derivatives, which is what you see here. All sorts of operators, 7 pages of them. Okay, so as I said, the discussion that I now enter into is based on this paper. What does this paper do? It completes the list of these sort of operators that was started by Babu and Leung. It provides an algorithm, develops an algorithm for tree-level openings of those operators, deriving those operators from underlying renormalizable UV complete theories. And this algorithm has been validated for example, against dimension 6 SMEFT. The subsequent theories that you get, which include neutrino mass theories, are filtered, and I'll explain what this means later on, to produce genuine neutrino mass models. you can study the statistics of the properties of these theories because you have kind of constructed all of them. Based on these techniques, completely new models are constructed, although I won't have time to talk about that. John has made a code available online for community use and also searchable database of all of these models. And also I'd like to emphasize that all of these techniques can be used for any sets of effective operators, not limited to the Majorana neutrino application. And I give some references here to where you can find these online tools. So first of all, let me review how you open up the Weinberg operator. So if you open it up at tree level and you look at all possible minimal ways that you can do that, you get the three well-known tree level seesaw mechanisms, type 1, type 2, type 3. And it's just a matter of seeing what are all the underlying renormalizable interactions involving exotic fields that when you integrate out those exotic fields, you produce this operator at low energies, and you get precisely these three. So the beauty of starting with effective operators and opening them up systematically is that you construct all the theories, and that's something we want to do. Here is an example of opening a more complicated operator that's not in the Weinberg class. It's this particular one, O12A, with lepton doublets, quark doublets, right-handed up quarks, and some isospin structure. And here's a figure that shows you the different pathways to opening up this operator. Here's the effective operator. And as you move down this path here, eventually when you get down to the bottom, you've completely opened it up by introducing three scalars that Yukawa couple with the fermions. And then the three scalars have a cubic interaction with themselves. This is one path to opening up this operator. And there are others, the starts of which are indicated in this light gray. And there's even one here which uses a vector boson in the completion, indicated in red. So a given operator generally has many ways of being opened up, just like the Weinberg operator produces three tree-level seesaw mechanisms. For the rest of this talk, I'm going to ignore the ones that involve vector bosons because, you need a Higgs mechanism. There are all sorts of complications to do with the model building that I don't want to get into. Once you've opened up the operator, then you need to turn it into a Majorana neutrino mass diagram. So here's an example of how you do that with another one, operator 11, with this particular flavor structure. And you see that you need to take the D bars and the Qs, and Yukawa couple them to Higgses in the usual way. And then you get a self-energy graph that gives you a Majorana neutrino mass. So this effective operator gives you the Weinberg operator at two-loop level. And then once you have opened up O11 itself at tree level, this means you have a two-loop model for neutrino mass. Okay, so opening up these operators brings you into the subject of radiative neutrino mass models. And radiative neutrino mass models are interesting for many reasons. First of all, they do explain tiny neutrino mass for a number of reasons. First of all, there is a seesaw effect. The more massive you make the exotics, the smaller is the neutrino mass. There are loop factors, and there are also products of coupling constants that could be all slightly less than one. Here I refer to a review. So you obtain a lot of models of this kind. You obtain what I call a discretum of these models, and the tree-level seesaw models are just at one end of this spectrum of different kinds of models. All right, now let me explain filtering. So when you open up an operator, it produces a set of sets of exotic field content, and these are called unfiltered models. With that field content, you can then write down the most general renormalizable Lagrangian, which will be some Yukawa and scalar Lagrangian in our case. Sometimes baryon number will be violated and you have to impose conservation, so let's do that. But then you have to be careful because it can happen that the resulting interactions from this most general Lagrangian generate the largest contribution to neutrino masses from an effective operator that is not the one you use to derive the field content. So then what you should do is re-tag that model against the dominant operator, not the operator you happen to use to derive the field content. And when you do that, we get filtered models. Okay, and there are some assumptions we make about the filtering, like no special hierarchies of parameters. And also, we have to use some of the Valencia work to do some additional filtering because we don't look at loop level completions.
Ray,
okay,
if I might, you have 6 more minutes.
Yes, thank you. When you go through that exercise and you do it systematically, you can produce tables like this, which have each operator, and then we have the number of unfiltered models associated with each operator. Then after filtering, you see that a lot of the models disappear. The next column tells you at how many loops neutrino mass is generated. And then the last column says that if you put all dimensionless couplings equal to 1, what is the scale of new physics? And you can see that the scale of new physics can go all the way from about 10 to the 12 TeV, which is what you get for the seesaw models, down to much smaller scales like 1 TeV down there. And there are also some operators that produce no filtered models and are therefore irrelevant for neutrino mass, it would appear. And I should point out that the historically relevant Z-Babu model is associated with this operator. This is the way it happens for this model, which you may be familiar with. You open it up with 3 scalars, and then you close off these external lines, and you produce a 2-loop neutrino mass diagram. And then the other interest in these radiative models is that these exotics, this doubly charged K and singly charged H scalars, can be searched for at the LHC. So we have complementary ways of probing the origin of neutrino mass. How many models do you get? Well, you get thousands of models. So in terms of unfiltered models, 140,000 up to mass dimension 11, and then 11,000 after you do the filtering. And you can see how the models vary with the mass dimension of the operator, and you actually get more of them at higher mass dimension because of the combinatorial explosion. You can do all sorts of statistics. You can work out with order 1 couplings what sort of scale of new physics is implied by operators of different mass dimension, and the widths of these flatworms, as I like to call them, tell you how many operators contribute to a neutrino mass which is driven by fundamental physics at, say, 10 to the 5 TeV. That's given by that width. You can look at what sort of exotics you get, in our case, scalars and fermions, and you can see the most common situation is to have 5 exotics. You can look at how many exotic fields in general you get in these models, and the answer is somewhere between 2 and 6. Okay, you can investigate what sort of quantum numbers you get for the exotics. In the case of scalars, you get a lot of leptoquarks, you get diquarks, you get dileptons, you get some other types of scalars, and you get vector-like fermions of various kinds, colored ones, lepton-like ones. And amongst the scalars, amongst the leptoquarks, there are ones called S1, S3, and R2 that also have different names in the SNEF literature that are of great interest for the B meson anomalies, S1, S3, and R2. And then S1 and R2, subset of these, are also of great interest for G-2 of the muon and also the electron. And this table tells you what their quantum numbers are and what they couple to if you're not familiar. You can also investigate which exotics occur together, and you can do this beautiful diagram that John did of how things are connected. And the 10 most common exotics that occur together are listed in this table. And so the idea is, I suppose, if you were to discover an exotic and you were to discover another exotic, and it happened that it was part of this table, that would be suggestive that those might be responsible for neutrino mass. You can ask questions like, how many economical and testable models are there? Namely, how many models have less than 4 exotics, and also a reasonably testable scale of new physics lambda of 100 TeV. And if you make dimensionless couplings less than 1, the scale will be even lower. And here is the table of all such theories. And in this table, only one of the models was previously known. So there's value in doing this sort of systematic search. Now let me quickly move on to connections with G-2 and B mesons. You've all heard about the G-2 anomaly, big news this year. And as I've said before, these 2 scalar leptoquarks, R2 and S1, that appear very frequently in radiative neutrino mass models are of extreme interest for explaining the G-2 anomalies at 1-loop level. And there's a vast literature on this. And it's interesting that there is this connection with neutrino mass generation. Turning now to the B decay anomalies, we first of all have the neutral current anomalies, RK star, involving this ratio, which probes flavor universality between mu's and e's. And S3 can resolve these anomalies very nicely, and it occurs frequently in neutrino mass models. S1 contributes at one loop level and is marginal. R2 can contribute either at tree or one loop level, and I'll comment about that later on. So we need to keep track of this RK and also RK star anomaly and see if that develops in the future and it turns out to be a real anomaly and not just some kind of a glitch. Turning now to the charge current anomalies, RD star, which probe the universality violation between the tau and the E and the mu. Once again, the S1 and R2 leptoquarks can resolve these at tree level. The situation for R2 is a bit complicated in terms of resolving the anomalies and resolving them both together or not both together. Let me not go through that in the interests of time. So very quickly finishing up, can you do it all? Can you generate radiative neutrino masses, solve G-2 and the flavor anomalies? And the answer is yes, there are many ways to do it. We presented a non-minimal one involving S1 and S3, and then a massive fermion, which is needed to generate delta L equals 2 enhanced neutrino masses. But there are, when you do a search in the database, you find of order whatever this is, 250 models that contain the leptoquarks of interest that are also really key for generating neutrino masses. 2 of these 250 models have appeared in the literature, and we are currently studying this whole class. So let me conclude. So there is an exhaustive catalog and classification of radiative Majorana neutrino mass models. Software tool and searchable database are online. Scalar leptoquarks, diquarks, vector-like fermions are common exotics. The new physics scale is generically lower in these models than the tree-level seesaw mechanisms, and so searches at high-energy colliders and in flavor physics are relevant. Flavor physics is also relevant in terms of precision measurements, looking for anomalies, and specific models that combine all of the anomalies with generating neutrino mass have been constructed. And I have some avenues for further work here. Connection with dark matter, what happens to baryogenesis in the face of washout processes from this sort of delta L equals 2 things. What about flavor structure, CP violation effects? And I didn't get time to mention this, but there's also a potential role for effective operators of mass dimension greater than 11. So thank you very much. Sanjay, you're muted.
Thank you for pointing that out. Thank you, Ray, for a very good talk. It was a comprehensive analysis of discussion of a very general discussion of how to generalize the theoretical models that generate neutrino masses. I don't see any question in the chat, so I ask the participants, if you have any question, please put it down in the chat so that we can share it with the speaker. In the meantime, I can ask one question. You did talk about, so we have of the order of 10,000 models, yes, even after you've put the filter. Now you did discuss about possibility of explaining other anomalies like G-2 and the flavor anomalies that we have seen in our experiments. But then, of course, since these are very, very exotic models, you will also have constraints from non-observation of new physics in experiments. How do you implement that in the models, in filtering out?
Yeah, I mean, it's a good question. And of course you have to do it. And it's always a very detailed analysis. So far it's been mainly done on a case-by-case basis, looking at specific models and working out all the constraints and writing long papers where you look at all the pheno of it. It would be nice to have a systematic process for doing that. It's partially at least possible by taking the UV theory and deriving all the effective operators, not just the delta L equals 2 ones, but all the effective operators, and then looking at existing bounds on the Wilson coefficients of those operators. That's one way to approach it.
Yeah, so I mean, just like you have actually systemized the delta L equal to 2 operator, you can also systemize all possible operators that will give signal that are supposed to give signal and we haven't observed them.
Yes,
that would then filter out some of these models because they are kind of ruled out from other experiments.
Some will be ruled out and some will have their parameter space constraint.
Yes, they will have the parameter space constraint.
There are other things to look at too, like direct production of exotics at the LHC and so on.
So I have a question from Yasaman, and I'll read it out to you. So she says, to explain the G-2 anomaly with leptoquarks, how large the new coupling should be?
Not so bad. So S1 and R2 do G-2 at loop level, and the special thing about S1 and R2 is that they have both left Yukawa couplings both to left-handed quarks and leptons and right-handed ones, and that means that there are quark mass enhanced contributions from those leptoquarks. So that helps to keep the coupling constants under control.
Okay, so we are bang at 3 now, and I don't see any further questions. So thank you, Ray, for a very nice talk. And I now invite Livia Ludhova to tell us about solar and geoneutrinos. So can you share your screen, please?
Yes.
Perfect. So, yeah, absolutely.
Okay. Okay. Hello to everybody. First of all, I would like to thank the organizers and the Borexino collaboration that I am representing for giving me the possibility to present this talk. It will be divided in 2 parts. The first one will speak about solar neutrinos and the second one about geoneutrinos. I will introduce and motivate each topic, and then I will give the most recent and relevant results from Borexino, Super Kamiokande, and Kamland experiments. So let's start with the topic of solar neutrinos. As we know, the sun is powered by the hydrogen to helium fusion, which in 99% of cases proceeds via the well-known PP chain. It's only the subdominant order of 1% of occurrences that this fusion is catalyzed by the presence of the carbon, nitrogen, and oxygen. The relative ratio of these 2 processes strongly depends on the temperature in the core of the star. And in the massive stars, which have higher temperature in their cores, the CNO cycle is the dominant energy producing process. What makes is also the main hydrogen to helium conversion process in the stars in the universe. Along each of these processes are emitted solar neutrinos, which have their characteristics energy spectra, as we can see on this log plot. The highest flux is dominated by the lowest energy PP neutrinos. Then we have monoenergetic lines of beryllium-7, PEP neutrinos, and the boron-8 neutrinos represent the low flux, which extends up to the highest energy point of about 15 MeV. The lowest flux is expected of the HEP neutrinos, so this is the only species which has been not experimentally observed so far. The CNL neutrinos are emitted from 3 interactions which have very degenerate and similar shapes, and in the analysis I will present, they are summed and weighted according to relatively well-known ratios. By these arrows are shown the roughly the threshold of the experiments which are currently measuring solar neutrinos. It is the Super Kamiokande water Cherenkov detector in Japan, which is making the boron-8 neutrinos above the threshold of about 3-4 MeV. Borexino is a liquid scintillator detector in Italy, which succeeded to lower the threshold in such a way that can perform observation and measure all solar neutrino species. Both experiments show solar neutrinos via the elastic scattering of electrons in the target material. This interaction has no threshold and is sensitive to all flavors. However, the electron flavor has the cross-section, which is about 6 times higher and thus the overall observed rate depends not only on the flux, but also on this flavor composition. In addition, even monoenergetic neutrinos are measured in terms of a continuous spectrum of the scattered electron, which has a characteristic well-defined energy. To measure solar neutrinos today is motivated by learning both about the neutrino physics, in particular about the oscillation parameters and about the matter effects, and eventually for searching for non-standard neutrino interactions. But also we obviously learn about the solar and generally about the stellar physics. Neutrinos are the only direct probe of the nuclear fusion powering the sun, and represent also the test of the thermodynamical stability on the longer time scale. Particularly important problem is the so-called solar metallicity problem. Metallicity is the relative ratio of the elements heavier than helium with respect to the hydrogen, which is the input parameter to the so-called standard solar model. This parameter changes the opacity of the sun and thus the temperature on which are strongly dependent the cross-sections of the nuclear reactions and thus indirectly also the neutrino fluxes. It is only the case of the CNO cycle which is directly influenced by the presence of the metals by which this process is catalyzed. The issue now is that the low metallicity inputs, which are based on the updated spectroscopic analysis and 3D models of solar atmosphere, spoil the previously observed agreement of the standard solar model using older high metallicity spectroscopic data or analysis, which were in agreement with seismological data. As it can be seen on this plot showing the fractional sound speed difference as a function of radius, shown for the older models in blue and for the new low metallicity standard solar model in red. This table compares the predictions of the solar neutrinos for the two categories of the standard solar models, and we can clearly see that for the CNO neutrinos, this difference amounts to about 30%. So let's have a look at the solar neutrino Borexino detector, which is the world's radio purest liquid scintillator detector containing about 280 tons of target, held in a very thin, ultra thin nylon vessel. Characteristically, the solar neutrino analysis is performed in the wall-less fiducial volume defined within the liquid scintillator target. Borexino started data taking in 2007, and in its first phase observed the first solar neutrinos. Then followed an extensive liquid scintillation purification campaign, which further reduced the radioactive background. The phase 2 from 2012 to 2016 was dedicated to a comprehensive spectroscopy of PP chain neutrinos. Then since 2016, we are in the phase 3, which is dedicated to the observation of CNO. Borexino was awarded in 2021 by the European Physical Society the Giuseppe and Vanna Cocconi Prize for the groundbreaking observation of solar neutrinos. In addition, here at TAUP, Borexino is releasing the first directional detection of sub-MeV solar neutrinos and the measurement of the beryllium-7 rate in the phase 1 when the calibration with gamma sources had been performed. So let's have a look at the PP chain latest results from Borexino. The rate of the PP, beryllium-7, and PEP solar neutrinos is extracted by a multivariate fit of the energy spectra. The interaction rate of boron-8 neutrinos above the 3.2 MeV threshold is extracted by a fit of the radial distribution of events. These results led to twofold main results. There is by comparison of the beryllium flux measured with 2.7% precision and boron-8 with 8% precision, Borexino slightly prefers the high zeta standard solar model. This preference is decreased when the boron 8 results from a Super Kamiokande and Snow experiments are taken into account. Borexino observed for the first time the PEP neutrino with more than 5 sigma confidence level and measured the electron neutrino survival probability for all solar species. And like that, observed the conversion from of the oscillation survival probability from the vacuum to matter-enhanced region, and excluded at 98% confidence level the vacuum LME, the pure vacuum oscillation. The challenges to measure the CNO solar neutrinos are several. First of all, the rate of CNO neutrinos is low, and its spectral shape has no prominent features. And in addition, the shape is correlated with PEP solar neutrinos and with the bismuth contamination of liquid scintillator. The PEP solar neutrino can be constrained, its rate, of course, to 1.4% from the solar luminosity constraint and global feed of solar data, of course, excluding Borexino phase 3 data. The expected sensitivity for the high zeta standard solar model CNO prediction and conditions achieved of phase 3 concerning the constraint of bismuth and PEP, the expected sensitivity is 4 to 5 sigma. So what is the main strategy, how to constrain the bismuth, the necessary condition to make a high sensitivity observation of CNO? Bismuth, which is anti-correlated background to CNO, is a daughter of lead-210, which by itself is not a dangerous background because it emits low energy electrons, and is a long-lived element, is constantly producing the bismuth, which by itself then decays to polonium-210, which is alpha emitter, and finishes in a stable lead-206. Now, thanks to the existence of the alpha-beta pulse shape discrimination technique, we can event by event take polonium events, and in the condition of the secular equilibrium of this chain, the observed number of polonium events corresponds to the rate of bismuth-210. In reality, of course, the situation is more complicated due to the fact that polonium-210 is contaminating also the inner vessel which is holding the scintillator. And the seasonal convective currents occurring inside the liquid scintillator volume were bringing the polonium by detaching it from the vessel and bringing it to the fiducial volume of the solar analysis. This is demonstrated at this plot, showing the polonium rate in different covers from the bottom to the top of the detector as a function of time. We can clearly see the strong correlation, time evolution during the phase 2 of the polonium rate, which is correlated with the average detector temperature shown in red. And only in the phase 3, we see that the polonium rate overall decreased and the seasonal modulation is strongly suppressed. This was achieved thanks to the thermal insulation of the detector installed by the end of year 2015, and then the temperature probes, some of which were an active temperature controllers of the detector. Like that, we succeeded to establish a stable positive vertical gradient along the detector, which substantially blocked these convective currents. Thanks to this, in the core of the detector was created the low polonium field, from which we have studied and in which we fit the distribution of polonium. And we extracted the minimal value of polonium, which is then considered an upper limit on the bismuth. Since we cannot exclude the residual contribution of the polonium being brought to the low polonium field by residual convective currents to the low polonium field, this number on the bismuth is represented as an upper limit. Nevertheless, when this number is applied in the multivariate fit, along with the constraint on the PEP neutrinos, we could extract the high significance measurement of CNO neutrinos. If you are interested to learn more about this, the technique of this multivariate fit or the threefold coincidence method, I invite you to follow these additional contributions here at TAUP. So here are the final results. The measured CNO rate is in a good agreement with both low and high zeta standard solar model. But we have confirmed that the null hypothesis is excluded at 5 sigma significance. And this measurement represents the first experimental evidence of the existence of the CNO process to occur at the nature and constrains its contribution in the sun to a value of about 1%. Borexino is performing also releasing new result on the directional measurement of sub-MeV solar neutrinos, and in particular performing the angular analysis of the first and second hit of each event from the region of interest around the beryllium 7H from the phase 1 of Borexino data. And by performing the fit with the Monte Carlo PDFs is doing the force detection of the directionality of sub-MeV solar neutrinos and overall of the neutrino elastic scattering in a liquid scintillator detector. By subtracting the expected CNO and PEP contribution in this region of interest, we measure also the beryllium sun rate, which is an agreement with the prediction and the spectral fit of this data. So this analysis is the proof of principle for future detector that such analysis can be used to measure solar neutrinos, but what is essential is a dedicated directional calibration in order to improve the precision of such measurements. SuperCam Kande has also provided and updated measurements. Thanks a lot to Metallicity for providing and discussing the results with me. In the phase 4, they improved the removal of the cosmogenic radioactive events and increased by 12% exposure. And they measure impressive almost 6,004 boron-8 solar neutrinos in phase 4. They also improved the energy reconstruction, retuned the energy scale, and improved the detector simulation. Like that, they updated the fit to solar neutrino oscillation parameters. And what has particularly changed in the best fit value of the solar mass splitting. The previously observed tension of the mass splitting released by Kamlan, so by the measurement of reactor antineutrinos, which was at the level of 2 sigma, is now decreased to about 1.4 sigma. Important to know that addition of the SNO results to this global fit, the precision on the mixing angle improves, however, does not change the conclusions of the mass splitting. Decay also studied the matter effects, both in the core of the sun by studying the energy dependence of the energy spectrum and of the electron flavor survivor probability. And the data favor the MSW spectral distortion at 1.2 sigma level. SuperK studied also the matter effect in Earth. So the increased rate of the boron-8 neutrinos during night when the electron flavor is regenerated during the passage of neutrinos through the Earth. They observe 2.1% plus minus 1.1% day-night asymmetry. So let's move to geoneutrinos and let's have a look how neutrino physics can understand the origin of the energy driving many impressive and sometimes dangerous processes on the Earth. From the measurement of temperature gradients along the boreholes, geophysicists estimate the integrated surface heat flux to be 47 plus minus 2 terawatt. There are two main contributions to this energy. In green is shown the latent heat from the time of accretion of the Earth, and in red is the radiogenic heat. While the contribution from the lithosphere is relatively well known, what is the very uncertain is the radiogenic heat coming from the mantle. And exactly the mantle radiogenic heat is the parameter which is the main goal of the measurement of geoneutrinos. Geoneutrinos are antineutrinos from the decays of long-lived radioactive elements as uranium, thorium, and potassium. While their abundances in the Earth are directly correlated to the released radiogenic heat in an easy way, in order to predict the geoneutrino signal and also to interpret the measured geoneutrino signal in terms of radiogenic heat, what comes into the play is the distribution of radioactive elements, and some assumptions on them must be done. In this sense, the neutrino geoscience is a truly interdisciplinary field. I would like to mention also that due to the chemical affinity, particularly of uranium and thorium, which are refractory and lithophile elements, they are concentrated in the crust, in particular in the continental crust. They are at the ppm level, large volume of the mantle. They are expected to be present, but at several orders of magnitude of lower concentration. And in the core, metallic core, nothing is expected. I have to mention also the bulk silicate Earth models, which predict the average composition of the silicate Earth. They use various information in input, including the observed correlation between the isotope ratio to silicon of the elements in the sun and in the chondrites. Assume such trends also in the primitive Earth. Like that, these models predict also, the average composition of the present-day remixed crust and mantle. And by subtraction of the known, relatively well-known contribution of lithosphere from the predictions of this model, one can extract this large interval of the mantle radiogenic heat from 1 to 27 terawatt, which can be split to various categories of the BSC model, low, middle, and high. Geoneutrinos are detected via the inverse beta decay interaction, sensitive only to the electron flavor, and having a kinematic threshold of 1.8 MeV. This kinematic threshold leaves potassium-40 geoneutrinos undetectable, and we measure only the high energy tail of uranium and thorium geoneutrinos. The request of the delayed coincidence between the prompt and delayed signal is a strong background suppressing tool, and the energy of the prompt positron signal is directly correlated to the energy of the incoming geoneutrino. It is often useful to express geoneutrino signal in the terrestrial neutrino unit, where one TNU represents one IBD event for about 1 kiloton of liquid scintillator target in 1 year with 100% detection efficiency.
Livia,
so have a look.
You have 4 minutes.
Yep. Yeah, thank you. Let's have a look at the latest geoneutrino results. Borexino released the latest results exactly 2 years ago at TAUP with the paper published early last year. There is a dedicated parallel talk. And we have measured 53 geoneutrinos with 18% precision. Kamland released the latest preliminary result in the Neutrino Geoscience Conference in 2019. Thanks a lot to Hiroko Watanabe for providing their results. And measured with 6 times higher exposure than Borexino, 170 geoneutrinos with 16% precision. Borexino is performing a simple analysis of the spectral fit of the prompt energy spectrum with completely reactor-free background, reactor-free contribution in the fit. Kamlan is performing the complex rate, shape, and time analysis. The sensitivity of both experiments to the with this exposure to thorium and uranium mass ratio, which is important to test the Earth formation processes, is limited. Concerning the mantle signal, the key process, the key element is to understand the contribution of the continental crust around the detector. Geological studies around the experimental site were performed both by around the Borexino and around Kamland. Borexino performed a dedicated fit in which the lithospheric contribution, so crust proofs upper rigid mantle, was constrained. the resulting non-zero mental signal was observed for the first time at more than 99% confidence level. The extracted radiogenic heat of 25 plus minus 10 terawatts corresponds to the uranium and thorium radiogenic heat from the mantle. The same number extracted by Kamland by direct subtraction of the expected crustal contribution from the measured overall signal is 5.4 terawatt. So let's have a look at the comparison of the Borexino-Kamland results, also in terms of comparison with respect to geological expectations. Overall, there is a general agreement of the data versus BSC models, and this is must be considered as a big success both of neutrino physics as well as geochemical modeling. However, there is some tension between the experiments if we assume laterally homogeneous mantle. While Borexino excludes the observes a tension at 2.4 sigma level, with the models predicting the lowest uranium and thorium abundances, Kamland prefers exactly this class of BSC models. So this brings me to the conclusion. We have discussed solar and geoneutrino results. Borexino performed a complete spectroscopy of the PP cycle and discovered the CNO solar neutrinos. However, more precise measurement as well as improved precision of the standard solar model are needed for solving the solar metallicity puzzle. Unfortunately, Borexino will stop data taking shortly, in the order of a month or so, and more precise CNO results are very hard, but not fully excluded. We have also released the first information about the directional detection of sub-MeV solar neutrinos. Super K also updated the boron 8 analysis. Geoneutrinos are observed with high statistical significance by Borexino and Kamland, and the two results are in some level of tension, assuming laterally homogeneous mantle. I would like to bring to attention also the parallel talk about the ocean bottom detector, which would be, in my view, really the ultimate experiment to measure geoneutrinos from the mantle. So I thank you to the attention, and I highlight other talks, especially about the next generation experiments in Juno, Snowplas, and Hyper-K, which have solars and eventually also geo among their goals.
Thank you, Livia, for your presentation. It was very nice. I see one question which I am going to read out to you. So Takahito Hachia asks, does directional information also help CNO study in Borexino?
For now, we have studied this only as a proof of principle at the high signal of beryllium 7H. If this can be used for CNO, it's the next step that we want to test. We don't have a clear answer for now.
Is there any other question? You can quickly type in chat. If not, I can ask this. So understanding the sun is just as important as understanding neutrinos. So it's very interesting that Borexino is giving results where we can distinguish the high metallicity sun from low metallicity sun standard models. You showed results separately for PP and for CNO. Do you also have combined results which tell us which of the two standard solar models are preferred?
All standard solar models, low and high metallicity, predict both PP and CNO solar neutrinos. So as you can see here, both categories of solar models predict PP neutrinos as well as CNO neutrinos. And the most precise results we have obtained for PP neutrinos in phase 2. There was not possible due to the thermal instability of the detector to measure the CNO. And in the analysis, the CNO flux was constrained, which, however, had no impact on the observed values of other PP neutrino species. And in phase 3, we succeeded to observe geoneutrinos, but we focus on that. And the problem is also losing the PMTs, which makes the observation of the lower energy part of the spectrum somewhat difficult. So especially for PP neutrinos in phase 3, it's really difficult. But we are considering to do a combined global feed of all phases at the end of the experiment to see what can be done exactly in a combined analysis as the final Borexino results for all fluxes.
Yeah, so, and also, I mean, like superchemical results also you showed, is there any plan to do a combined analysis with their data as well?
Well, this we did not discuss, but I mean, concerning boron 8, I mean, their results is just much more precise. I mean, we measured we measured to slightly lower value. So the threshold is 3.2 MeV. Their threshold is 3.5 MeV. But their statistics is much higher. I think that what was unique in Borexino is to see in one detector the survival probability for all flavor, for all solar species. So finally, we can see that the PA is not flat and it's not a vacuum only level, but a precision measurement of boron 8 neutrinos only. I think, I mean, there we are, there the error is by far dominated by SuperK.
So there is one more question, which probably we can still take because we are not running very late. So Ibrahim Mirza asks, please explain use of nylon foil in Borexino.
So nylon is the about 100 microsyn balloon, which holds the scintillator and separated from the buffer liquid, which has the same density, but serves as a shield against the external radiation, but it's not scintillating, especially to protect the higher trigger rate due to the radioactivity in the PMTs. So it's a mechanical holder of the liquid scintillator target. I don't know if there are more questions on that. I'm happy to answer.
If there are more questions, of course.
Okay.
Well, there is one more question from Bhavesh Chauhan. He asks, can electron scattering be used to detect low energy geoneutrinos?
Not really. I mean, the geoneutrinos have flux which is orders of magnitude lower than solar. So while they react with elastic scattering, their flux is much lower with respect to the solar neutrinos and other backgrounds. So I mean, there is no possibility, in my view, to measure their contribution from the spectrum of the singles. I mean, we measure 50 geoneutrinos in more than 10 years with the IBD, which has 100 times more interaction cross-section than the rest. So we would have one event of scattering of geoneutrinos. I mean, plus there are potassium-40 geoneutrinos, but still within all reasonable geological models accepted by geologists, the scattering of potassium-40 geoneutrinos would not produce any easily detectable signal.
Okay, so there is another question, but I think, Bhavesh just says thank you to you. Thank you, Livia, from all of us for a very exciting talk and discussion.
Thank you very much.
We will meet again at 4 for the next session.